Recording in progress.
Hello, folks. Welcome to our next major topic in Chem 220, which I am titling here Solubility Equilibrium. And what I really appreciate about this topic is that foundationally, all the principles that we're going to talk about and all the concepts we're going to explore when talking about solubility equilibrium have not changed from our prior conversations about things like solubility and things like equilibrium. So, what we're doing in this next section is we're taking what we already know about how substances dissolve and what we know about how systems establish an equilibrium to describe what happens when an ionic substance or a salt dissolves in solution. So it's kind of like a good capstone to equilibrium, in my opinion. Ooh. So let's start with this tried and true image we've seen a bunch of times in my class of sodium chloride dissolving. So let's remind ourselves about what happens when an ionic compound dissolves in water. So recall that ionic compounds, which we casually refer to as salts, dissociate or split up when dissolved in water into the cation, the thing that is positively charged, and the anion, the thing that is negatively charged. And these ions are able to actually exist as ions in solution because there are intermolecular forces that exist between the dipoles of the water molecules and these ionic charges on the ions themselves. So our ions are hydrated, or in other words, solvated via dipole intermolecular forces of water surrounding those ions with some kind of three-dimensional arrangement. So looking back at our sodium here, so this sodium cation over here on the right, notice that all of the dipoles of water are organized so that the partially negative region of the molecule is attracted to that positive charge. And that this organization is innately different from what we see for the chloride anion, because the anion is negatively charged. And so when the water molecules surround this, we see that they do so in a way where the positive end of the molecule, the water molecule, is now attracted to that negative charge. And these both create what we call, like I said, hydrated ions. So this right here is kind of like review, right? This is how we understand the idea of an ionic compound dissolving in water, starting from I think week number 2 of this class. So then what is new? What is different about what we're talking about when we discuss ionic solubility and solubility equilibrium? So as it turns out, this process of dissociation, or as we've called it, dissolution or hydration, exists, capital backwards E, exists on a spectrum that is unique to each salt, meaning each salt from sodium chloride to magnesium sulfate, etc., has its own unique degree of dissociation at some particular temperature. And we see this when we think about like trying to dissolve different substances. So we had a lab where we looked at the dissociation of silver acetate. So we utilized in that reaction a beaker that had silver ions, and then we added thiocyanate ions. And we noticed that when those ions navigated toward one another in solution, they became so closely associated that they went from being in the aqueous phase to now being like that solid, cloudy chunks that we saw in our beaker at the end point. And we know innately that something like silver thiocyanate is less soluble, meaning has a tendency to not be dissolved or hydrated or dissociated in water than something like silver acetate. So we describe this like difference in innate dissociation as being the solubility of our salts. So each salt has a unique degree of dissociation, which means that each salt has some unique dissociation equilibrium that describes it. So this is very similar to our conversation about acid strength and that degree of dissociation. So when we talk about weak acids, just a reminder, weak acids are those that have acid dissociation constants that are small. So when we're thinking about that acid as being one that gives up its proton in solution or dissociates in solution to create hydronium, that degree of dissociation is what we called like how strong the acid was, how effective it was at putting hydronium in solution. Here, it's a very similar idea. If we're talking about a dissociation capacity, then the degree of dissociation is linked to some kind of equilibrium that we can quantify and describe and explore for how this ion, so here like the sodium chloride crystal and its ions, are dissociated and then also reassociated with one another in solution. This is what makes it an equilibrium. So how do we describe equilibrium? First, we need to understand the context in which this equilibrium between our solid and its aqueous ions exists. So let's first describe a saturated solution. So define a saturated solution. This is a solution that contains the maximum number of moles of solid salt, right? Solid ionic compound. So a solution that contains the maximum number of moles of solid salt, which in turn means that this is a solution that has kind of reached its hydration capacity, meaning we've got like the maximum number of ions that can be hydrated by the water in our solution. So when we're talking about ionic equilibrium, we have kind of like two ends of the spectrum to think about it. The end of that spectrum is going to be this idea of saturation. So let's kind of go through conceptually and like graphically what's going on when a salt begins to dissolve, and then what happens when we approach this idea of saturation. So for any salt, regardless of its like dissociation strength or equilibrium, the moment that you put it in water, there is going to be some like initial dissociation, right? So we've got like some initial, just when that crystal hits the water, what's going to happen to those ions? Those ions are going to be driven into the aqueous state, meaning like the rate of dissociation is going to jump ahead of the rate of reassociation. So we have a large degree of dissociation. So this forward part of being dissolved, like if we're going from solid to aqueous ions, this is what's favored at this condition, initial conditions. So now let's look here at what happens as we continue to add salts. So we are adding salt and we are dissolving more and more of our ions. So the salt continues to dissolve. However, as that dissolution process continues, so does the number of ions in solution begin to increase. So we see like more ions dissolved, and then we establish or begin to establish an equilibrium. So we undergo some change to get to equilibrium. So we can see this here with this little pictorial representation of some salt crystal that while we do indeed have crystals that are then becoming free ions in solution, some of those ions are actually reassociating with the bulk larger crystal structure and reforming the solid, meaning that we do overall favor the forward reaction, but the difference between here and here is actually not that large, meaning like here we have a rate of forward that is approaching almost equal the rate of the reverse, or the rate of dissociation equaling the rate of reassociation, whereas here we were very, very like dissociation driven. So in this case, the degree of dissociation changes, and where we were once primarily ion driven, we now are like still dominantly ion driven, but now with some non-zero like reestablishment of that crystal back to its solid phase. So then let's take this a step further. What happens once we've reached the saturation point? So at saturation, our solution cannot dissolve any more solid salt, meaning like we have maxed out the number of ions that we have in solution. So we would see something like, again, our solid at the bottom of our beaker. But this solution, if we were to zoom in very, very close, we would see that it has like a large amount, certainly larger than prior states shown to the left, of ions contained in it. So I would have things like many more of these purple ions and of these red. But since we here at saturation have hit like the maximum number of ions that the solution can contain, we finally achieve a state of equilibrium between the solid phase and the aqueous phase, meaning equilibrium where the rate of the forward and the rate of the reverse process are equivalent. So for everything that is dissolved or dissociated, there's a reassociation back into the solid crystalline structure. So here we have the max degree of dissociation achieved. And this is where we are indeed at a phase equilibrium. So we would see a constant exchange of ion and solid at equal rates in solution. So this is what it means to be at saturation. And at saturation, like physically in the lab, you will always observe solid in your solution. That is the only way that this statement up here can be true. If we have the solid phase, aka the crystal solid salt, existing in equilibrium with its ionic form, meaning its dissociated ions, then when I look at a saturated solution, I had better see both of those physical phases represented. So I should see a solid crystal as well as my saturation point where I have hit my max number of ions dissolved in water. Now, this is something that we have said exists in a state of equilibrium, right? So this is kind of following through from initial dissolution to like early dissolution to the hit point of saturation where we now have equilibrium. So let's maybe apply some of our skills in describing systems at equilibrium that we've seen in other chemical contexts to what's happening in this state of saturation. So the state of saturation is where the equilibrium is established. So just like with any other state at equilibrium, whether it's an acid dissociating or some general gaseous reaction occurring, we can describe that by using some equilibrium constant, K. So we can describe the degree of dissociation of a salt in a saturated solution where we have solid in equilibrium with aqueous via an equilibrium constant, which we here call KSP. So just like Ka meant the dissociation constant for some weak acid, and Kb, the dissociation constant for some weak base, KSP is an equilibrium constant, but it now has a little bit of context. So SP, we'll talk about that. So let's consider some general salt, X2Y3, solid. If I dissolve this and allow ions to dissociate to the point where I've reached saturation, meaning I now establish an equilibrium between my solid and aqueous phase, according to the meaning of these subscripts, I'm going to generate a certain number of X ions. So it's going to be 2 X ions and 3 Y ions, where these charges of these ions are something that we inferred based on what these subscripts were. So they were multiples of one another. So remember, at saturation, we have an equilibrium that is established between the solid and the aqueous. So let's see if we can't maybe construct an ice table, because that's how we understand getting from like an initial state, like starting to dissolve something, to this equilibrium state, and then relating that all to some equilibrium constant K. So the unique thing that is like inherent or intrinsic in all ionic solubility equilibrium expressions, like these ice tables, is notice that we are talking about one of those phases in this equilibrium as being one of the condensed phases, the solid phase, meaning that any expression of what's happening with the amount of the solid is not included in our ice table. So initially, this is going to be like early dissociation times, like we've just now put that crystal in, right? So we've got 0 amount of ions. And then over time, we're going to utilize the stoichiometry of this dissociation to describe like how the amount of X is going to increase and how the amount of Y is going to increase so that ions do exist in solution, meaning some of that solid does get dissolved. So looking at my X ion, I'm going to create, maybe X and Y was a bad choice. Let's maybe call this AB, just so we don't have too much alphabet soup going on here. There we go. So looking at my cation, right, because stoichiometrically I generate 2 of these from every one of my solids dissolved, I have to indicate that in my change. And same deal goes for my anion, B2 minus. I'm going to create 3 of that. Where if you want to think of it, this would be like minus X. So for like every amount of solid that's dissolved, I generate twice that amount of A and 3 times that amount of B. That's what this is saying here. Which means that at equilibrium, I've got 0 plus 2x or 2x and 0 plus 3x or 3x. And if I were to write an equilibrium expression, KEQ, this would be concentration product to their coefficients over concentration reactant to that coefficient. And for us here, our reactant is our solid phase, so we only have our products to consider. So this is equal to the concentration of A3 squared and the concentration of B2 cubed, where these are the equilibrium concentrations, because we're relating this to an equilibrium constant. And if I plug in my ice table values, I get 2x squared times 3x, let's see here, cubed, yeah, sorry. Make sure my 2's and 3's are accounted for. And this would be 4x squared times 9x cubed, or 36x to the 5th, where x is equal to that amount of our solid dissolved, right? The change from our solid into its ionic phase. So why do we have this thing, aka this equilibrium constant, that now has a new name? So KSP is also called the solubility product, because of this statement that we made up here. If X is the amount of solid dissolved, then that has to be innately related to the amount of ions in our saturated solution or our dissociation equilibrium. And it's called the solubility product because it is going to relate to this idea of solubility, right? Amount of ions comes from amount of solid, which relates to solubility. And it's a solubility product because we have products that have solubility relationships that are then being multiplied. So the solubility product constant is what we call KSP, which is the equilibrium constant that describes ionic equilibrium. Dissociation equilibrium of ionic salts. A bunch of different ways to say that. So in our next video, we are going to talk about this idea of like solubility, because we've described The idea that like once we're in this state of saturation, we have hit our maximum number of solid that was dissolved. And this is something that we are going to relate to a quantitative like number that we say like, oh, this is how soluble you are. Because if one salt dissolves more, then I can put more solid crystals in the solution and have that dissolve fully compared to a less soluble solid, which will dissolve less. I could put less of the solid in the solution and have that dissolve. So next video, we're going to kind of explain this idea of like what is solubility and how this relates exactly to the amount of ions in solution coming up next.